Welcome back. In this section, we're going to look at inverse functions because our ultimate goal is to define an exponential function as the inverse of a logarithm. So before we can do that, we have to talk a little bit about inverses. Some of the discussion will be things that you'll remember from pre-calculus, but we're also going to go deeper into calculus ideas, the relationship between the derivative of f and the derivative of f's inverse. So things that we'll know from the past, if you have two functions and if you stick one inside the other and they essentially cancel each other out and give you just x back, and the same thing happens if you stick the other function into the first one, you get x back. If that's the case, then what you've got is two inverse functions. In other words, f composed with f inverse should give us x, and f inverse composed with f should give us x. Usual notation, f inverse with a little -1. Of course, if the opposite of f is f inverse, then the opposite of f inverse must be f. So in other words, the inverse of f inverse is f. Inverses are unique. So if I find the inverse for a function and you find the inverse for the same function, we should find the same thing. There shouldn't be two different answers for what is the inverse of f. Okay, so without having talked about how to find inverses, we can at least confirm that these two functions are indeed inverses, that g is the inverse of f. And I can see that just by looking at f composed with g. If I put g of x inside of f, so if I'm putting that 7x to the 5 plus 3 inside of f, then I would have fifth root of, instead of x, it would be fifth root of all of this business, minus 3 over 7. And you can see after a couple of lines how things are going to clean themselves up. The 3 minus 3 will cancel each other out immediately, and then I'll have 7x to the 5 over 7, and the 7's cancel, and then I've got a fifth root of x to the 5, and the fifth root and x to the 5 cancels, leaving just x. And similarly, if I did the reverse, if I looked at g composed with g composed with f, so in other words, if I put that fifth root inside of g, then what I would have is 7 times, instead of x to the 5, it would be 7 times that fifth root to the 5, with a plus 3 at the end. And then basically same thing is going to happen as before. The fifth root and fifth power would cancel each other out. And then the dividing by 7 and multiplying by 7 would cancel each other out. And then the minus 3 and the plus 3 would cancel each other out, leaving us with just x. So when we put g inside of f, or when we put f inside of g, each time we got x as our end result, so therefore g must be the inverse of x. This is another property that we had from before. This is one that you would remember from pre-calculus as well. It's a graphical relationship. Is that if you've got a point that's on the graph of f, then by switching the x and y coordinates, you get a point that's on the graph of f inverse. And that's at least the graphical interpretation of it. So if we're thinking in terms of the overall shape of our graph, that means that basically what we're doing is we're switching x's and y's, or we're reflecting our graph in the line y equals x. Of course, when we say something like AB is a point on the graph of f, we're saying f of a is equal to b. And when we say BA is the point on the graph of f inverse, we're saying f inverse of b is equal to a. So let's start off with this. I can say, suppose that I'm trying to prove this statement. I need to start off with assuming that f is a function and f inverse exists. So let's suppose f has inverse, f inverse. We're trying to prove an if and only if statement. We're trying to show this point is on the graph of f, if and only if the other point is on the graph of f inverse. So basically, I have to show two things. if AB is a point on the graph of F, then I can conclude the other point is on the graph of F inverse. And I'll also have to show if this is a point on the graph of F inverse, then AB must be a point on the graph of F. Both are relatively easy to show. So first I'll say, let's suppose AB is on the graph of F. And we're trying to show that BA is on the graph of F inverse. So the question is, what is F inverse of B? Well, good news, we know what B is. B is the same thing as F of A. We said AB is on the graph of F. In other words, F of A is equal to B. So this B that I have here, I can replace it with F of A. Oh, and there we go. F inverse and F are canceling each other out because they're inverses, so we get A as the end result. So in other words, if B is going into F inverse, A will come out, or in other words, BA is on the graph of F inverse. And now the reverse is also pretty much the same. Suppose that we have BA is on the graph of F inverse, and we want to show that AB is on F. So we say, well, let's look at F of A. Oh, what is A? Well, interestingly enough, it's F inverse of B, and that's because BA is on F inverse, so F inverse of B is A. I can replace A with F inverse of B. And F and F inverse cancel each other out as they always do, leaving just B. So if we put A in for F, B will be the thing that comes out. So in other words, AB is on the graph of F. So there we go. If you have an xy point on the graph of one function, then by switching those coordinates, you have the point that's on the inverse. And we're going to see this in action. I'm going to graph both of these functions. I first want to quickly confirm that they're inverses of each other, and then I'm going to graph them on the same axes. So first, if I'm looking at f composed with g, so in other words, putting that cube root of x minus 1 into f, I can see I would get that cube root cubed plus 1. And I can see really quickly the cubing and the cube root are going to cancel each other out. The minus 1 and the plus 1 cancel each other out, leaving just x. And same thing is also true when I do the reverse, when I put f inside of g. For that, I'm putting that cubic function, x cubed plus 1, inside of g. And that means I'm going to have in my cube root, instead of x minus 1, it'll be x cubed plus 1 minus 1. The plus 1 minus 1 cancel each other out, and I've got cube root of x cubed, and that is just x. So there we go. We've now confirmed that g is going to be the same thing as f inverse. And now if I'm graphing these two functions, I mean, I know what x cubed looks like. This is an x cubed graph that's been shifted up by 1. So normally when you graph an x cubed graph, you have the points 1, 1, 0, 0, and minus 1, minus 1. I'm going to shift those points all up by 1, so I'll have 1, 2, 0, 1, and negative 1, 0, and that would be my graph. There we go. Just label that point. That would be my graph of x cubed plus 1. The other graph that I'm graphing is the cube root of x minus 1. And that's a cube root graph moved to the right by 1. The cube root also passes through those three good points, negative 1, 1, 0, 0, then 1, 1. But I'm going to take that graph and shift it all to the right by 1. So when I graph my cube root of x minus 1, I'll have the point 2, 1, 1, 0, and minus 1, 0. And so I wind up with this is my graph of cube root of x minus 1. And we can see that, yeah, the property of switching x and y coordinates has happened. 1, 2 is on the graph of one function, and 2, 1 is on the graph of the other. We've got 0, 1 versus 1, 0. We've got minus 1, 0 versus 0, minus 1. And if we sort of tilt our heads at a 45-degree angle, we can see that the shapes are indeed mirror images of each other. So yeah, as expected, the graphs have that nice little reflective property that they're essentially reflected in the line y equals x. Okay, of course, if you're remembering back to pre-calculus, you know that when we were talking about inverse functions, it was only really for one-to-one functions. So we need to know how to show that a function is one-to-one. Definition for a one-to-one function is that different x values will give you different y values. So one definition would be to say that if you've got a one-to-one function and you know that you've got two different x values, then you would have to have two different y values. Or you could say the reverse would be if the y values you picked were the same, then you would have to be thinking of the same x values to take you there. That's another equivalent way of showing that something is one-to-one. So that means we've got really two approaches. We could start by suppose we've got two different x values and then hopefully conclude that we get two different y values, or we could start by supposing we've got two identical y values and showing that that must lead us from two identical x values. So for this one, I mean, it's pretty obvious from what we remember from pre-calculus that this should be a one-to-one function because we know what this should look like. It should look like a x cubed graph that's been moved to the right and vertically stretched and shifted downward by 1. And we probably have a nice intuition that, yes, it would certainly be a one-to-one function. But I want to be able to show this algebraically. So here's what I'm going to do. I'm going to start off by supposing that I have two identical y values, and I'm going to show you that that means I have to have two identical x values. So I'm going to suppose that f of x1 and f of x2 were equal to each other. F of x1 would be this function evaluated at x1, so 5 times whatever x1 is, minus 1 cubed minus 1. And f of x2 would be my function evaluated at x2, so 5 times x2 minus 1 cubed minus 1. And I'm going to add 1 to both sides of the equation, so that gets rid of the minus 1 on both sides. That turns out kind of nice. I could also get rid of the 5 by dividing both sides of the equation by 5. And I could also get rid of the cube by taking cube root of both sides. Just as a little side note, the reason why, of course, this is going to be fine for me to do is because I know for cubes, if I have some number cubed equals to some other number cubed, that there's not two different answers for what would the cube root be, as opposed to squares. If I said x squared was equal to some number, then x would have two possibilities. It could be plus or minus the root of whatever that number was. But when we have x cubed being something, there is only one answer for what x is, and it is just the cube root of whatever that number happened to be. So if this was a square, then what I would be doing next would be worrisome. But because we've got cubes, then I can confidently say that x1 minus 1 and x2 minus 1 must be equal. And so now I can add 1 onto both sides of the equation, and I can confirm that x1 must be equal to x2. So if we thought we had two identical y values, the only way that that would happen would be if you had two identical x values. So therefore, f is 1-to-1. All right, a little bit of terminology to introduce here. So monotonic functions, these are functions where if you're monotonic, then f of x1 will always be greater than or equal to f of x2 for any points you pick, or f of x1 will always be less than or equal to f of x2 for any 2 points that you pick. It's not quite the same as saying increasing or decreasing because we're allowing that the y values could be the same. So for example, if you had a function that went upwards for a while and then was a horizontal line for a while and then went upwards for a while, that would count as something as monotonic because no matter which 2 points you pick any 2 points you pick on this graph, the one y value will always be greater than or equal to the other y value. So in other words, when I pick a lower x value and a bigger x value, the bigger x value has greater than or equal to y value than the other one did. So for any two x's that you feel like picking, the f of x1 and f of x2, if we're looking at x1 being the smaller number and x2 being the bigger number, in this case our function is like either increasing or constant. The other option that you could have, of course, for something being monotonic would be something that's either decreasing or constant. So an equivalent graph that went down for a while and was horizontal, then went down and was horizontal, that would still count as being monotonic because pick any two x values, and for that one, the left x value would have the bigger y value, bigger than or equal to the one that's on the right. So we're allowing 2 points to have the same y value or allowing 2 points to have different y values. But it's basically when we say something is monotonic, we mean that you are either increasing or constant or you are decreasing or constant. If we wanted to rule out the being constant, then we would say you are strictly monotonic. So pick any two x values there where x1 is less than x2, and we'll always have it always increasing or always decreasing. So strictly monotonic functions, something like y equals x cubed, that's always increasing. Even y equals cube root of x, that's always increasing. And we actually proved earlier that logarithms were always increasing. That was kind of a nice thing that we showed back at the very beginning of 5.1. So we could say that the natural log is a strictly monotonic function.